Now we will discuss on the chapter 11, GIS data projection and coordinate. So when we talk about the GIS, we are talking about the location of the real world, and we cannot escape from the coordinates and projection. So what is coordinate system basically? So when we talk about the features on the earth, we know that our earth in the sphere surface, if we are not living in the flat world. Okay, remember, so features on the spherical surface are not easy to measure. Can you imagine if you have this kind of football, a big football, very big football, how you want to measure from one distance to another distance? You have to measure it manually, right? So if it is too far, it is impossible for us to measure it manually. Therefore, we have to represent the world in specific in mathematically to identify where our location is. Okay, so features on the planes are easy to be measured and calculate. Of course, you want to calculate distance, angles of area. Is very easy on the flat surface on the paper, as opposed to a spherical areas. Therefore, coordinate system provides a measurement framework, and two map layers are not going to register spatially unless they are based on the same coordinate system. What does it mean here? It means that if you have one map is in Kuching and another one will be is in Kuala Lumpur, I want to make sure, make clear that Peninsula Malaysia and Sabah Sarawak, both of us are using a different coordinate system, surprisingly. Alright, so it is quite impossible for us to combine the map together, because different system, if you try to put it together, it tells you different location. Okay, therefore we have to try to standardize the coordinate system, where we uses the more generic one, such as the latitude and longitude, where it is also being used over the world. Okay, so the geographic coordinate system is the location reference system for the spatial features on the Earth's surface, and the geographic coordinate system is defined by the longitude and latitude. Okay, there are a lot of different type of coordinate system. There are arbitrary coordinate system, global Cartesian coordinates for the whole world, geographic coordinates for the whole world, and also the projected coordinates on the local area of the Earth's surface. Okay, the arbitrary usually is being used by the AutoCAD system, where it has its own origin. Okay, and also the raster data. However, this one is the one that we use, is the what we call here as a geographic coordinate system. This is the one where we trying to represent our world as a perfect round sphere. However, our world is not perfect sphere, but mathematically we assume that our earth is perfect, and by giving the locations based on the grids of the degree, minute and seconds, we can locate where our locations are. Okay, by having a prime meridian and equator, okay, as a representations of the left and of the right. Okay, the north pole to represent the north and the south, and the angle locations can be determined, thus shows where we are. Okay, so these are the geographic coordinate systems that we use. Okay, so geographic coordinates, the starting point of the measurements for both latitude and longitude differs, where for the longitude it is based on the Greenwich meridian, which is the starting 0 point degree of the calculations, while for the latitude is our equator, right? And if we are here, okay, the location will be determined by the longitude, okay, the angle of where we are from the starting point to our point, and also the latitude from the equator to our point. Therefore, we will have something like north how many degree, how many minute and second, and also east how many minute, degree and second. This will be our locations in the geographic coordinate system. So in order for us to represent our world in the mathematics, therefore we have something called Earth datum, and Earth datum defines the standard value, okay, of the ellipsoid and the geoid of the world. And latitude and longitude are defined using an ellipsoid, where ellipsoid is rotated about an axis, and the elevation is defined by using the geoid of the surface, where they have the consistent gravitational potential. So how to measure the latitude? For taking our point S here on the surface of the ellipsoid and define where this is a tangent of plane of M and N. So the angle of theta will be defined based on our tangent of the location, and also the gravitational point where it is our geoid. Therefore, we can have our location in the latitude. So for the longitude, however, is the value of longitude is the angle between a cutting plane of the prime meridian, which is the 0 here, and the cutting order through the point of P here. So we will calculate it here, and if we are going in the other side, will be in negative, so it considered as a west, and if going for the right side, will be on the east side. Okay. However, for the Cartesian coordinates is where we're trying to make it from the sphere into a planar mode. So a planar Cartesian coordinates is defined by a pair of the orthogonal x and y axis drawn through an origin, where it is something like we see in our map on the paper. This is the Cartesian coordinates. However, it doesn't really represent the shape of the real world, as we're trying to put it in the planar mode for the whole world. Okay, and how those geographers approximates the Earth? When we try to come up with this coordinate system, we have to represent our world in something that mathematics can understand or can calculate. So the simplest model to approximate the Earth is a sphere, where it was typically used to discuss the map projection, as what we discussed before. But the Earth is not a perfect sphere, where the Earth actually is wider along the equator than between the poles. So basically, it's just like an oblong shape of the world. Okay, therefore, a better approximation of the shape is called a spheroid, also called as ellipsoid, where its ellipse rotated about its minor axis. And to best represent the real world is through datums. So datum is a mathematical model of the Earth, which serves as the reference or base to calculate the geographic coordinates of the location. So in datum, basically we have a datum to represent the whole world, and also the datum to represent a local area. So a shift to the datum will result to the shift of the positions, and this models the shape of the Earth's surface, where it is used to increase the accuracy for the local area. So this is how basically our world looks like. And in order to best estimate the world, so we assume that our world is something like this. It's a spheroid or ellipsoid, where it is best to be determined or to be modeled using the mathematics, as opposed to this kind of shape, where This is for the WGS1984, which is what we use for the coordinate system. However, for the real world, it's something like this. That's why if you are using the GPS and using the WGS1984, you might as well get some error data due to the difference of the datum settings. Bear in mind. Okay. So in order to translate the shifting of the Earth, so we are using these translations of the three kinds of parameters from the shifting, rotation, and also the ratio V. Okay. So through these transformations, so the shift of the surface, the surface to best represent the local area is very important. Okay, and it depends on the location on the datums actually, and it is not consistent. Therefore, different country might have a different datum in order to estimate its local projection. Now we are talking about the map projection. So what's basically a map projections is a systematic arrangement of parallels and meridians to convert from the spheroid ellipsoid space into a flat surface. Why we do that? Because we're trying to simplify the map into a simple representations that users can use it. Okay, and it's easy to calculate the distance, area, as well as the perimeter. So the cartographer will group the map projections by preserving the property into the conformal, equal area or equivalent, equidistance, and azimuthal or true directions. Therefore, how the cartographers do it? They uses a geometric objects like a cylinder, cone or plane, and a globe to illustrate how to construct a map projections, such as this. For the areas that are within the northern hemisphere, a simple case or secant case of the conic is best to represent how we want to flatten the Earth. However, for the areas that are within the equator, the cylindrical will be the best to project the areas into a plane surface. However, for the areas they are quite small, azimuthal is what they being used in order to project the actual surface into a planar surface. So why we do the projections? Because we want to convert our Earth location, the features, into maps where maps are flat. The idea of having maps is because it is easy to carry, good for measurement, and is scalable. And map projections are used to project data from a sphere into a planar surface. And usually for map projections, they always introduce error and distortion, because how possible if you want to convert or you want to trace from the curvy areas into a plane area is quite difficult. So that's why there are some distortion. So distortion can be minimized in one or more of the following properties, such as for the distortion of the shape, we use the conformal of the area where it's more or less confirming the actual shape on the real world. For the distance, we estimate is using the equidistance, where it's a plus minus more or less the same distance as on the real world. True directions, we still kept the true directions because our north is not going anywhere, it is same north. And for the area, we make sure it is within the equal area. That's why in the map it might show the area might be the boundaries. We're trying to preserve as good as possible the boundaries from the map into the real world. So for the plane rectangular grids, it provides an easy use collocation system that does not require corrections for the curvature of the Earth, where the measurements are specified in terms of distance from the origin, when typically measured north and east of the point. Okay. Of the origin lies outside the area being mapped is called a false origin. Okay. So for the topo surface, where the Earth surface or using the Earth GPS is something like this, but when you use the geoid from the mean sea level, there are some differences of the altitude, and for the ellipsoid based on the datum is something like this. That's why in projections and coordinates, to ensure the accuracy of the altitude is and elevation is very difficult due to this kind of nature. So in Malaysia, we do have our local projections. For Peninsular Malaysia, we have our RSO Kertau 1948, okay, and of course for the Sabah and Sarawak, we have our BRSO Timbalan 1968. Okay, it's quite different from the one that we use for the land and survey, because for the land and survey, the coordinate has been encrypted with extra values on top of it, on the first coordinates. That's why if you're using the GIS, you cannot simply just opening the data from the land survey and using it to do the analysis. You have to decrypt it first, convert it into the ArcGIS coordinate, then you can convert it into the geographic coordinate, so that you can combine it with the peninsular data and also our other world data and also your GPS data. That's very important, right? And now of course we have the local projections based on the GPS, which is GDM 2000, but it still not covers the whole area. Okay, alright, now we are talking about the georeferencing. Georeferencing is a process to transform a spatial data set, usually raster data, from an arbitrary coordinate system into a geographic or map projection coordinate system. This georeferencing, usually when you have a scan map or you have this aerial photo, we do georeferencing to increase the accuracy of the data. So a set of ground control points is required as a link between the arbitrary coordinate system and the geographic coordinate system, where those ground control points are something that you can find on the ground, or you can collect it by using the GPS by your own. There's no automated ground control points. So a mathematical equation is commonly constructed based on the type points to complete the system geometric transformation from the arbitrary coordinate system to the geographic coordinate system. Okay, so during the process, it's not that we are just pulling the string from A to B. No, it's something, it's quite complicated, where the computers we calculate based on the root mean square error. Okay, so all the movement, X, Y, and Z movement based from the georeferencing will be calculated and determine its accuracy. Okay, the higher the accuracy, the better, but it's more tedious. Lower the accuracy, no need to use lah. Okay, so georeferencing is also known as a registration, co-registration, or geometric transformation in a different context. And in order for us to do the georeferencing, we have to come up with our own ground control points. We have to go to the ground, pick up your GPS, take the point, and key in the data. So ground control points are also known as a type points, stick points, conjugate points, where it's a point on the Earth's surface where both image coordinates, measured in rows and columns, and map coordinates can be identified on the ground and also on the image. So GCPs are points of the image whose position can be referenced to a known coordinates or to the same points on the geocode image. So location for you to use the ground control points, or we call it GCP. GCP can be easily and clearly identified. It must be easy to identify. It must be clearly identified. It must be precisely located. Okay, it must be visible. It must be small, not too big. It must be stable. Okay, we don't want to collect it by today and by tomorrow it's already vanished. It must be permanent, and also must be something that are well defined. Other people also can find it. So the ideas will be, we are using the road intersection, the runways. Usually we using this human-made features as opposed to the natural features, and we trying to get the fixed areas, rigid features. Not you don't use cars to georeferences, or you use goats or cows that are whoring around, eating grasses to use the GCPs because it is not static. We don't want to use that. Okay. So the distribution must be fairly uniform. Example here, it must be, let's say this is the map of the area, so we must have one point on the left on top, one point on the left of the down, right on top, and also right below. It must be well distributed. Minimum 4 is good. You have more than 4, 6, 10 is good, and must have a regular pattern, cover as much as image can be, and it must be evenly distributed. And the double GCP depends on the terrain, the size of the image, and the rectification method and the order of the mathematical equation. Okay, if the image was distorted or it was taken when during the image taking, the platform have some shaky, so more GCPs are required. So acquisition of the ground control points, it could be based on the topographic map or survey maps, and the good one would be based from the GPS measurement. So the acquisition of GCP is manual and based on the visual inspection. That's why it's good that if you are the one who go for the GCPs, you are the one who go for doing the georeferencing, because you have the experience and the familiarity of the area. Okay, if a geocoded image exists, automated image matching can be utilized. Okay, however, the best one will be the ground points, the ground survey or GPS measurement. That's the best one, but the others will be some alternative. And of course, even though we are trying as much as possible to ensure the accuracy of the data, there will be some error. So because of the map registration is a statistical process, therefore there are some lack of fit or error in the process because of the coordinate error, pointing error, blunders during the process, because our hands are shaky, our eyes, we do have uneven, we have some problem with our eyes, or taking alcohol too much, media distortion, or it could be because of the systematic error due to the platform or due to the camera distortion. And all of this will be summarized by the residuals by using the root mean square error, where it is a statistical measures of the error between the calculated coordinates of the GCP from the fitted polynomial equation and the measured coordinates of the GCP from the GPS or topo maps and more. And the least square fit methods is used to fit the transformation parameters. At least one ground control points more than the minimum. Minimum is 3. You must have 4 to generate a Ramesh error. The polynomial will not transform every GCP to be 100% accurate. And it's important before the full rectification to ensure the error are within the acceptable limits. We don't want to have too much limits, but having this decimal number is good enough. So the polynomial will not transform every GCP with 100% accuracy, and it's important before the full rectifications proceed to ensure that the error are within the acceptable limits. So there are limits, we don't want to have more than limits. Okay, and the root square error value for each GCP will affect and is affected by other GCPs. So it's very important to ensure that all the GCPs are in the correct order, is widely distributed, because it will, if for every GCPs they are wrongly a point, even 1 or 2, it will increase the probability to have a higher error. So how to calculate the transformation error? So these are the formula. And remember, for root mean square error, it must be below than 1. It must be 0 point something. If you have more than 1, therefore you have to redo all over again. Thank you very much.